Okay, we'll what are we talking? We're talking Monte Carlo, Markov chain Monte Carlo. Huh? And in particular, we're talking about the Metropolis algorithm. And then right now we have kind of a discrete case, right? Discrete case, we've got 7 islands. Do you guys remember this example? Mm-hmm. Okay, and then the island populations are proportional to their number. So if I just said, what's the probability of landing on island 7? Well, first we would need sum of 1 through 7. Sum of n from 1 to 7. And what is that? 8 times 4 times 28? Yeah. And then so, the probability of being on 7 would be 7 out of 28. And then the probability of being on 6 would be, 6 out of 28, so on and so forth. Okay, et cetera, et cetera, et cetera. So, and in our current algorithm is flip a coin to decide to go left or right. Okay, compare the proposed island population to current island population. Okay. And effectively, I mean, the population is pretty much a proxy for probability, right? So we can say, compare the probability of being on the next, the proposed island versus the current island, right? And so kind of the probability of moving is going to equal the probability of the proposed island. So I'm going to say theta proposed divided by the probability of the current island, theta current. However, if the proposed island is bigger than the current island, this will give you a ratio bigger than 1. So we say the move is going to be either this or 1, and it's the smaller of these two, right? Meaning if the proposed island is bigger than a current island, then we move with probability 1. And if the proposed island is smaller than the current island, we move with the probability of this divided by this. Yeah? Okay, so if proposed is greater than current, move with probability equal to 1. And if proposed is smaller than current, move with probability equal to probability, theta proposed divided by probability of theta current. And that's basically it. And we just repeat. Yes?
What about on the ends?
On the ends, you can pretend you have island with 0 population, and you have another island with 0 population. Meaning, if you propose moving, like you flip the coin, and it says you move to the right, you say, well, I'm not moving to the right, I'm going to stay, right? Because you calculate the probability of the proposed versus the current, and that's going to be 0. So you move with probability 0, which means you remain. Okay, and we drew, we drew some pictures, and we said, okay, if we start off at island 4, on the next turn we can end up at island 5 or island 3 or even at island 4, right? So let me pull that picture back up. Actually, let me see if I can go back through the. Where is it? Okay, so I'm going to copy this stuff. All right, let me show you what this. So we did this a little bit, with the pictures here. Okay, and let's just say we got what do we call this vector? Do I have a name for this vector? All right, I'm just going to call this the theta vector, okay? Maybe this is not correct, but we're going to start off, our original theta vector is going to be 0, 0, 0, 1, 0, 0, 0, right? And this represents the proportions or the probability of being on islands 1 through 7, okay? So this is represented by this. And then to illustrate how I went from here to here, I'm going to multiply. We're going to take our theta vector and we're going to multiply it by our transition matrix. Let's see, what letter do we call our... Oh, okay, sorry, this is not our theta vector. This is our W vector, okay? Sorry. So this is our W vector. Okay, and we're going to multiply it by our transition matrix. Okay, so what is my transition matrix? All right, for now, let's just focus on the the column for the 4 here. Okay, so for the 4th column. Okay, so this is, because really that's the only column that matters, right? Where is it? Hang on. So I multiply this by, let me just think. Oh, I'm sorry. Each row, we're going to look at, where we are in the current row, and then where we end up in the next position here. Okay, so we can say, if I start off in position 4, okay, so we'll look at the fourth row here. So 1, 2, 3. Wait, hang on. Let me pause. Okay, the transition matrix. Let me back up here. Okay, so the transition T matrix. Each coordinate, right, is the row represents your current position, and the column represents your kind of the next position. And thus the position third row, second column, okay, row 3, column 2, this represents the probability of going from island 3 to island 2. Okay. Sorry. So each spot represents, okay, if I'm currently at this island, what's the probability I end up going to the next island? Okay, so if I'm currently at island 3, what's the probability I go to island 2? So right now, it's just what is the probability of going from island kind of 4, 1, 2, 3, 4. So if I'm currently at, this will be row 4, and we can talk about if I'm in row 4, you know, column 1, 2, 3. So columns from island 4, I cannot go to columns 1 and 2, right? Or islands 1 and 2. So those probabilities will be 0. Okay, but from island 4, what is the probability I end up going to island 3? So, you know, column 3 will be, I have to have, the coin has to flip with probability 0.5 pointing to island 3. And then once it points to island 3, what's the probability I actually move to island 3? Yeah, it'd be 3/4, or I'll do probability of kind of theta island 3 divided by probability of theta island 4. Okay, so this is kind of my column 3. And then, what is the probability I remain? So, well, let's go to the island to the right. Okay, first it has to point to the right, probability of 0.5, and that's it actually, because if it points to island 5, I'm going to go there. Okay, and that happens with probability 0.5 with flipping there, and so therefore the island probability remaining is going to be 0.5 times 1 minus probability of theta 3 divided by probability of theta 4. Is that okay? So this is my transition matrix probability for row 4, and this is the probability from going from row 4 to island 3, probability of going from island 4 to staying at island 4, and the probability of going from island 4 to island 5, represented by this row here. Yes?
Just out of curiosity, this is kind of like unrelated, but is there any relation to from Markov chains to random walks?
Yeah, they're very similar.
Okay.
Yeah.
I didn't know if they use some of the same like concepts, or if they were, if one was like.
This is essentially a random walk. Okay, so the question is, are Markov chains related to random walks? And the answer is yes. Okay. This is effectively a random walk, but it's not just purely random. Mm-hmm. There's a little bit of rules here. Okay, so if it was just purely random, meaning I flip a coin and I either go to the right or I go to the left, then I would visit all of the islands with equal probability, effectively. Okay, but then if I go according to these rules, then I will visit the islands in proportion to their population. Okay, so we're doing a random walk. Okay, so this is kind of the transition matrix just for from row 4 to just for this one. Let me, we're going to kind of fill out a little bit more of the transition matrix, and we'll generalize it just a tiny bit. Okay. So let's say this is our transition matrix. Okay. And then so here again, I'll be in row 4. So I've got a 0 and a 0 because I can't go to islands 1 or 2. And just in case island 3 is bigger, so now we're going to generalize to the case where the populations aren't necessarily in increasing order from left to right. We will say, so this will be kind of, generalized for, any population distribution among the 7 islands. Is that okay? And so, 0, this means not possible to go from island 4 to islands 1 or 2. Okay. And then what is the probability that we end up at island 3? Well, first we have to flip the coin, and it has to say go to that direction, go to the left. And then we're going to multiply this by the probability, the smaller probability of the island that is island 3. So this is the probability of island 3. And so we can say this is theta minus 1, meaning theta minus 1 means probability of the island to our left divided by probability of theta, kind of our current island. Okay, so that's the adjacent one, and then the island to the right is basically the same thing, 0.5 times the minimum of probability of the proposed island, which is to the right, theta plus 1, divided by the probability of theta. Is this okay? And then beyond this, it's just zeros, right? Let me see if I can squeeze this in. So this is row 4, column 3. This is row 4, column 5. Okay, and then row 4, column 6 and column 7 are both equal to 0 because you cannot transition from row 4 to 6 or 7. Okay, so then what goes in the middle? Well, it's everything kind of left over. So this is now generalized for any population distribution. So it could be bigger or smaller islands to the right or to the left. Okay, so we might remain if it proposes to the left and we don't move to the left, and we might remain if it proposes to the right but we don't move to the right. Okay, so this is going to be, can we draw a thin line to kind of separate here? Okay, so we've got, I will list this out. This is probability of propose to the left but don't move, plus probability of propose right but don't move. That's how we might stay where we are. And so this is going to be the probability of proposing to the left and not moving to the left is going to be what? 1 minus whatever this is. So 1 minus the min. So this, it looks a little scary, but it's not. Okay, it's just whatever this number was, we're doing 1 minus that. Meaning that if we move to the left with probability 100%, then this part's going to zero out. Okay? And then we add the probability of moving to the right, but not moving. So 1 minus minimum of proposing to the right, which is 0.5, but not moving, which is going to be 1 minus the probability of moving. Is that okay? And effectively, it's going to be the same for every single row, right? Except for row 5, it's just all of this is shifted over so that it's centered here in column 5. Okay, so each row is effectively the same, except we're just shifting everything over either to the right or to the left. Okay, what does it look like for kind of our last row? Okay, so we'll say, so columns 0 through, or columns 1 through 5 will all have probability 0, right? So for row 7, what do we have? So columns 1 through 5 will have a 0. Column 6 will have, what's the probability at column 6? 0.5 times the minimum of probability of theta minus 1 divided by probability of theta, comma 1. Okay, and then column 7, well, so column 8 is going to be a 0. Okay, and so effectively, that just eliminates this side, and that makes this side equal to this part just becomes this part becomes a 0, so it becomes this thing plus 0.5. Okay, so column 7 will be 0.5 times 1 minus this thing, 1 minus minimum of going to the left. I'll just write go left, plus 0.5, because all of this stuff just zeroes out. So that's what column 7 looks like. And then the same thing with column 1, it's just flipped around a little bit. Okay. Is this okay? So this thing represents our transition matrix. Okay, yeah.
For row 7, can we just say that column 7 would just be 1 minus that entire probability for column 6? Since we have no other options.
Yes, yes. They should be equal. I think, yeah. 0.5 times this, and then you add 0.5. Yeah, it just becomes 1 minus.
Okay.
1 minus.
And that would be the same thing with flip for column 1.
Correct, correct. Yes. Please see.
They don't move the islands because don't we flip a coin to see if they move left or right? So what is the instance where we stay on the island?
So there's 2 parts. We flip the coin, and the coin says call the island to the left and call the island to the right. Okay. So actually, it shouldn't be move to the left or move to the right. You flip the coin to propose the left or propose the right. Okay. So we flip the coin, we propose the left, and then to actually decide whether we go to the left or not, we called up the island and we say what's your probability or what's your population or whatever. Okay. So we get the probability of that proposed state, we compare it to our current state, and then if that proposed state's probability is bigger than our current probability state, we go there, okay? But if it's not, we take the ratio between our two probabilities, and then, you know, we get a ratio of 0.7, okay? Now we get a 0.7, then we, whatever, do a R-unit and see, you know, if it's smaller than 0.7, we'll go, and if it's not, then we stay. And so that's how we stay. We can stay if the proposed island has a smaller probability than our current state, and then after spinning, the thing didn't, you know, the probability didn't work out. All right, so this represents our transition matrix to go from one state to another state. So our Metropolis algorithm can be represented by our transition matrix. Is this okay? And then, so we can look at, with this transition matrix, what is our stationary distribution? Okay? And this is the reason why the Metropolis algorithm works. It's if we, we've reached our stationary distribution if, based on our current distribution, after multiplying it by the transition matrix, if we get back the same current distribution. Okay, so if this is our current state, generally after we multiply the transition matrix, we would expect something different from what we currently have, right? So if I multiplied my current state of zeros and ones and zeros, after applying the transition matrix, I'm going to end up having you know, something different than 0, 0, 1, 0, 0, 0. I'm going to end up getting this. After multiplying this state by my transition matrix, I will end up getting this. Okay? And after multiplying this by my transition matrix, I will get something else, which looks like the state 3. And at the very end, once we've converged to our stationary distribution, the idea there is I multiply by my transition matrix again, and it makes no change. Okay? And so we can kind of see, you know, if the resulting state, okay? So if my starting point, or my starting W, is equal to basically the probability of 1, the probability of 2, which is okay, so if this is the target distribution, right? If my starting state is the target distribution, okay, and I multiply W times the transition matrix, what we're going to end up getting is the resulting thing is going to be the same as our starting W, okay? Meaning that the transition matrix, if we plug in our target distribution and we multiply it by this, we're going to get the result. So this is, you know, if we begin with the target distribution, and multiply by the transition matrix, we get back the target distribution. Okay, and this means that the target distribution is the stationary distribution of our transition matrix. So that, okay, and so that's kind of why the Metropolis algorithm works, because the idea is, you know, if you keep applying the transition matrix, which is what happens, you know, if we let the chain run, you know, after 10,000 iterations, effectively you are just multiplying the transition matrix against your current distribution over and over and over 10,000 times, and it's going to converge to that stationary distribution. And if the target distribution is your stationary distribution, then that's a good thing. Yeah.
So target distribution is an eigenvector?
Yeah, the target the target distribution is an eigenvector of the transition matrix for the Metropolis algorithm. Okay, so that's why the Metropolis algorithm works, because the the eigenvector of the transition matrix is the target distribution. Okay, and so I don't think I have time to go through all of the math, but it's in the in that chapter right here. They go through the kind of the math to show that after you multiply the W by the transition, you get back the what you started with. Yeah. Yes.
Do you think of the transition matrix like conceptually like similar like to like a covariance matrix, for example?
Don't think of it as a covariance matrix.
I know there's not multiple like random variables, but like
no, it's a matrix showing if I start here, what's the probability I go to this next state? Okay, and so. So I don't. Some of you guys took my 102A class and you had to simulate Monopoly, right? And you wrote up all of this code to simulate Monopoly. Technically, you could create an entire transition matrix for the entire Monopoly board, all right? And basically it would be you know, a 40 by 40 matrix, okay? And if it were because there's 40 spaces on the Monopoly board, and if you start off at space 1, which will say go, then technically, and let's say we're not going to implement any rules, you cannot end up back at go, you cannot end up in space 1, but you can end up on the space 2 spots away with a probability of 1 out of 36. You can end up on the space with 2 out of 36, so on and so forth, until you get back to you know, 11 spots away and 12 spots away with probability 1 out of 36, and then 0, 0, 0, 0, 0, 0, 0. So it's the probability of, if I start at position 1, if I start at position 1 go, what's the probability I end up on, I don't know what spot this is, Baltic Avenue or something, and then this is you know, luxury tax or something, right? And or you know, income tax. You know, what's the probability of moving to each of these things? And then so this is kind of what it would look like. You have a transition matrix, and you build this up, and you have to implement all of the rules saying like, okay, if I start at this other location, you know, what's the probability I go from here, right? And so your chance if you start at chance, then the thing looks, you know, crazy and all sorts of stuff. And then so you have this transition matrix to say like, if I start at this location, what's the probability I end up somewhere else? And then you find the eigenvectors of this transition matrix, okay, which will give you the stationary distribution, and the stationary distribution of this grand transition matrix will also be the probabilities, you know, the relative probabilities of landing on each space. It will say like, at this point, you know, the stationary distribution will have jail to be the most frequent, and I don't know, something else to be much less frequent, and so on and so forth. Yeah.
Do you have to assume that it has like full rank? Like if there's like a 0 eigenvalue, does that mess it up?
If there's a what?
There's like a 0 eigenvalue in the middle, does that mess it up?
Let me think here. It's we call it it's the Markov chain is irreducible if from every location you can get to every other location. If there's a spot where you start somewhere and it suddenly becomes impossible to reach somewhere else, which is this 0 thing, then it's irreducible and I forget the exact properties of what happens, but yeah, we say the Markov chain is irreducible if you can start at any place and end up somewhere else, which would be the monopoly board, right? So, okay, we'll explore this with an actual example next week. So, all right, good luck, have fun at DataFest, you guys.